So welcome everyone, and welcome to the first TIA Centre seminar of this academic year. So for those of you that are new to our seminars, we aim to invite researchers and leaders in the area of computational pathology and associated areas to discuss their work. So my name is Adam Shepherd, and I'm a postdoc here at the TIA Centre. I know there's a few new faces online, so welcome to our seminars. And today I'm delighted to introduce Peter Neidlinger. Peter is a medical student at Friedrich Alexander University, Erlangen, Nuremberg, currently doing a research project in computational pathology under the supervision of Professor Jakob Kather at Technical University Dresden. He previously worked on his MD thesis about immunometabolism in colorectal cancer. His current focus is on weakly-supervised biomarker prediction from histopathology images with the goal of advancing foundation models in digital pathology. The title of Peter's talk today is Benchmarking Foundation Models as Feature Extractors for Weakly-Supervised Computational Pathology. Peter, thank you very much for joining us. We're really excited to hear your talk, and whenever you're ready, please get started.
Thank you very much for the invitation, Adam, and welcome everybody. So today I will talk about the main project I've been working here in the last 6 months in the Carter lab, and that's the benchmarking of histopathology foundation models as feature extractors for weakly supervised computational pathology tasks. First, I want to talk a bit about how this project came about and why I decided to do this project, and then how I designed it exactly, share some key results, and then a final conclusion. So the standard approach in computational pathology is that you have host-led images, for example, this H&E stained host-led image from colorectal cancer. And because these images are of gigapixel size, they are too large to be put into a model like this usually. So the standard approach is to tessellate it into many small tiles, and then each of these tiles is put through a model. But before that, the background tiles without any relevant information are removed. And so then you have all these tiles, and they are put through a model, and then you get these feature vectors. They are put together into a feature matrix. So now you have one matrix for the entire whole slide image. And then if you want to do some classification tasks, for example, predicting whether a gene is mutated or not, then you need an aggregator model, because you have like one feature for each tile, and you have to aggregate it somehow into one final prediction. And here in our group, we usually use STAMP, or standardized pipeline. And here the aggregator model is a transformer, but you could also use something like AdMill or some other mill approach. And of course, the question is, how do you get from these tiles to the feature vectors? And to do this, in the last few years, a lot of models have been published. For example, CTranspath already in the end of 2021, or also many others, especially in the last 12 months, Uni, Virchow, Prof. Gigapath, HOptimus, and many others. These are just some examples, and there are even more foundation models out there now. And then, of course, if you have so many models, the question is which one to use. And there have been some benchmarking studies already, for example, by Weiflein et al., by Jaume et al., and Campanella et al. And especially Jaume et al. Also used basically all of the recent foundation models, but it's always a bit difficult if it's not really an independent study, because then you can't be sure if there's no cherry picking of tasks. Also, if it's only on public data sets like the study by Weiflein et al., then there's always a minor risk of data leakage, because even though most of the foundation models say pretty clear which data was used, it's still better if you also have some private cohorts. And in the Computational case, they even say in the paper that they can exclude data leakage, so that the pre-training of the Virchow model was also partly the same data that was used for testing. And so while there have been some studies before, we decided that it would be very nice to have an independent benchmark by someone who didn't create a foundation model themselves in the group and also use multiple cohorts. And yeah, that's what we set out to do. And yeah, so the question was, with all these foundation models released in the last years, which one is the best? So we decided to take 4 different cancer types: colorectal cancer, breast cancers, stomach cancer, and lung cancer, and all in total 13 cohorts, some TCGA cohorts, some CPTEC cohorts, and then the proprietary cohorts DAX, IEO, Bern, and Kiel. And in total, we had 9,528 whole site images from 6,818 patients. And we decided to test them on multiple tasks. The main focus was biomarker tasks. Here in colorectal cancer, we looked at MSI status at BRAF, KRAS, ZIMB, and PIK3CA mutations. In breast cancer at ESR1, PGR, ERBB2 expression, and PIK3CA mutations. MSI status and EBV status in stomach cancer, and then EGFR, KRAS, STK11, and TP53 in lung adenocarcinoma. And then we also tried to look at some other task categories. We defined a group of morphology tasks, which is kind of loosely related. For example, in stomach cancer, the Lauren classification, which is a morphological classification, whether the cells look more like intestinal type or diffuse cancer. And in colorectal cancer, we had left-sided versus right-sided colorectal cancer, and then non-small cell lung cancer subtyping in lung adenocarcinoma versus squamous cell carcinoma. Then also some prognostic tasks, and that was whether the lymph nodes, if the cancer spread into the lymph nodes, or even if there are some distant metastases for end stages. And so in total, these were 31 tasks. And then, as I mentioned before, we have this standardized pipeline called STEM. And I added all these new foundation models there. So many vision-only foundation models, like starting with the TransPath, FECON, Dinos, SLPath, Uni, Virchow, Kaiko, etc. And then also some slide encoders. Recently, Madeleine and Prism were published in Chief. And also ProgGigaPath has a slide encoder as well. And then also some vision language models, Flip, Biomate, Flip, and CONCH. And then it was always the same setup. So I did 5-fold cross-validation, always training on 80% of the data and leaving 20% out for testing. And this was done on TCGA only. And then each of these 5 models I then externally deployed on the 5 external cohorts, so in CPTEC, DAX, Bern, Kiel, and IEO. And these were the metrics, so mainly looking at OROCs, but also at precision recall curves, at accuracy scores, at one scores, the lungs test, and Pearson's R for some correlation analysis, and did the lungs test for statistical significance tests of the OROC scores. And finally, some interpretability analysis using heat maps. For example, this is an MSI versus non-MSI heat map. Yeah, and with that, we can jump into the results section. So with all these heat maps, I normalized them horizontally. So this is just a lot of numbers and a lot of tasks and models. So I try to structure it a bit. And so the first thing I did is we don't want to see which task is the easiest and which task is the hardest. So I normalize it row-wise so that in each row, so for each task, you see which model performs best. That's the darkest model. For example, here, BHF2 and CONCH are the best models, and the lightest is the lowest score. So for example, here, BioMeClip and CLIP. Yeah, so in each row, there's always one light and one dark one. And then, of course, this always means something else. So here, a score of 0.72 is very dark, whereas here it's super light. So just that you're not confused. And then I also sorted the models by performance. So here are the best models, the highest average OROC across all tests, and here the lowest average OROC. And the best models, if you just look at biomarker tasks, were then BHF2, CONCH, ProgGigaPath, and Uni. And I just want to mention Panacea here as well, because this is a private model, and it's a bit special because it's actually not just one model, but two, because they have cancer-specific models. So it's actually a breast cancer model and a colorectal cancer model. So it's not designed for the other tasks, but it still kind of works for the other tasks. So I used the colorectal cancer model for the stomach adenocarcinoma test and the breast cancer model for the lung tasks. And yeah, since it kind of worked, and it was better to compare it if I tested on all tests, what I did. Yeah. And so what's also interesting is that the three vision language models are very different. So CONCH here performs very well, whereas CLIP and BioMeClip, which are also vision language models, are not so good. And if we look at the other two task categories, so morphology tasks and prognosis tasks, it's pretty similar. So CONCH and BHF2 are pretty good again. So if you look at the average across all tasks, CONCH is actually a bit better than BHF2. So the vision language model outperforms all vision-only models, but the difference is very small. And then yeah, similar models come after that. So the general patterns repeat. Here I show all models again and all tasks only a bit differently. In these stacked pie charts, the outer circle shows how many tasks the model manages to get an average OROC of above 0.7, between 0.6 and 0.7, and below 0.6. And so here it's sorted again by performance. So CONCH again the best, and then that's the worst model. And as you can see, CONCH manages to get an OROC of above 0.7 in more than half of the tasks, whereas CLIP only in less than 1/4. And yeah, on the inner ring, you see the different task types again. And you see that there are actually some quite large differences if you set thresholds like this. So CONCH is almost always above 0.6, only 4 tasks not, whereas CLIP doesn't manage to get over 0.6 in 12 tasks. Yeah. And here, this is a radar plot, again, showing all tasks, but this time only 4 models, the 4 best models. If you look at the average OROC across all tasks, and then this is again task-wise normalized. So there's always one model that is very close to the outer edge of the circle. And then in the middle is an OROC of 0.5. And yeah, then as you can see, especially for the high performance tasks where the models perform pretty well, there's mostly the orange one on the outside, that is BHF2. So BHF2 is performs particularly well on those tasks, whereas CONCH, the dark red one, performs particularly well on these low performance tasks. And that's something I also try to visualize here. Here I split the tasks into those where at least one model manages to get an average OROC of above 0.75 and below then on the low performance tasks. And here, if you just look at the high performance tasks, then BHF2 is the best one, followed by ProgGigaPath and CONCH. But if you look at the low performance tasks, so these are tasks where no model manages to get an average OROC of above 0.75, then CONCH performs best. And here it's interesting that Biomed-Clip is the third or the fourth best model in the low performance tasks, but pretty bad in the high performance tasks. Another thing I wanted to look at is the slide encoders. And the problem is that in the STAMP pipeline, this only works for mill approaches where you have basically tile embeddings and aggregate them somehow. And this was the main focus of the study. So I didn't want to use the slide encoders as they are mainly supposed to be used. So the main idea is that the slide encoders, they take tile embeddings from another model, and then they create one vector that is representing the entire slide. So for example, Madeleine takes CONCH features and then creates one slide embedding out of it that is task agnostic, so that can be used for any task, and same for the other models. But yeah, since in my pipeline it doesn't make sense to only create one slide embedding, you can also extract encoded tile embeddings from the slide encoders. So that's basically, I used those tile embeddings from CONCH, for example, and put them through Madeleine, and then extracted the encoded tile embeddings again. So from each patch of the model, again, extracted the embedding and looked at these performances, and same for the other models. And as you can see here is that the encoded tile embeddings from these slide encoders, they don't improve the performance. It's actually always a bit worse if you look at the average across all tasks. So it doesn't really make sense to use slide encoders in a setting like this. I also created a radar plot again here on showing the slide embeddings. But as I said, probably not so important because not the best way to use them. Where they are pretty good slide encoders is if you do linear probing only on a few cases, and then also using a very small model like logistic regression, something like that, and then they are usually pretty good. But if you have enough cases and enough compute, then you get better results with null approaches and tile encoders. I also try to compare transformer with abmil, because abmil is used more often in literature. And here the differences are pretty small, but also very similar for most of the models. So usually transformer is a bit better across all tasks, and usually about 0.01 for most of the models. So this depends on the number of patients you have available. Of course, transformer works particularly well if you have a lot of cases, but with my setup, it was already outperforming abmil. So I decided to stick to the transformer architecture.
Peter, so would you recommend for smaller data sets to stick with attention-based MIL?
If you don't have so much data, yes, then it's probably better. It's also faster. The transformer, is just taking more time than abmil.
And what would you class here as a large versus a small data set?
That's a good question. Probably also depends a bit on the task, but I think maybe between 100 and 1,000 cases is the cutoff. So somewhere in between, like if you go below 100 cases, then for sure abmil. If you go above 1,000, then surely a transformer is better. But the exact cutoff, I did some experiments with 75 patients, with 150 patients, and with 300 patients, and there I also tried both. And with 75 patients, abmil was better. With 300 patients, transformer was better, and with 150, it was very similar. So probably somewhere around that was the threshold to change.
Thank you.
You're welcome. Yeah, so then, of course, with all these results, the main question was, why are some foundation models better than others? Because yeah, we want to find out why some models are better so that we can design better models in the future. And what I looked at there is mainly the pre-training data set, because of course there are also some differences in the architecture. There are some vision transformer base models that are pretty small, like C-transpose, for example, and then there are also some vision transformers like H-optimus 0, for example, which are with giants, so much larger architecture, but yeah, the pre-training algorithm is usually very similar for the vision-only model. So the main thing that was different was the composition of the pre-training data set. And here, I always try to correlate some attributes of the pre-training data set with the average performance on my downstream tasks. And the first thing was the number of whole slide images that were used for pre-training and correlating that with the average downstream performance. And as you can see here is that there's a mild correlation, so it's between 0.4 and 0.5 for all task categories. So the more whole slide images you have, I mean, this goes up to 3 million here. This is VHF2. And the smallest model has only 5,000 whole slide images, I think. And the more you have, the higher the performance, but it's not a perfect correlation, of course. And I also looked at the number of patients. Here it's similar between 0.3 and 0.73, the correlation. Yeah, usually these correlations are not significant. And then also the number of anatomic tissue sites. Here the Pearson's R is between 0.58 for prognosis and 0.74 for morphology. And here, of course, there is one outlier, and that is VHF2 again. And yeah, that's really exceptional because for some models, they never state how many tissue sites they used, but VHF2 just used a lot more than all the others that we know about. So they used at least 175, but probably close to 200 tissue sites. And yeah, that seems to work pretty well. But of course, it's not only about the number of tissue sites, but also about the distribution of slides from each tissue. And that's something I want to talk about later. But first, I also looked at the vision language models, because these were only the vision-only foundation models now, because the vision language models, they're not really that easy to compare with the other models, because the image caption pairs, they are not whole slide images, but yeah, just some images, for example, from publications or from Twitter. And so it's, of course, not as much information if you just have a regular image compared to a whole slide image. And what you see here is that it's not all about numbers, because CONCH was vastly outperforming the other two models, and CONCH is this one here. So it was CONCH used, I think, 1.2 million image caption pairs, and BioMidClip used 15 million, so a lot more. But as I said, it's not only about the number, but also about the quality of how you filter these image caption pairs. And then, of course, it might also be differences in architecture. So here you don't really see any correlation between the number of image caption pairs and the performance. As I said, it's not just about the number of anatomic tissue sites you use, but also the distribution. And this data is not available for so many foundation models, but it is for Uni, ProgGigaPath, and VHF. And as you can see here, for Uni, it's pretty well distributed. So between 10% hard whole slide images, and then for bladder, it's like 1 or 2%, but yeah, it's pretty similar for all categories. Whereas for ProgGigaPath, it's over 40% lung and 30% bowel. And for Virchow, it's also mainly these 4 tissue sites that were used. And that seems to correlate with the performance. It's always better if it's more equally distributed. And that's what they also try to improve in the next generation in Virchow 2. And there they did some balancing of tissue sites. So for none of these tissue sites, they had more than 10% in the pre-training data set. And for rare tissues, they increased the number of samples. And yeah, so it was more well distributed. And as I said, they first had a lot of anatomic tissue sites, close to 200. And then they also tried to balance it more equally. And yeah, this seemed to be beneficial. And another aspect I tried to look into is how the distribution of tissue sites impacts the performance on these cancer types. So it's pretty straightforward that if you have a lot of lung cases in the pre-training data set, this might also improve the performance then on lung tasks. And for example, here, Prof. Gigapath, as I said, was trained on over 40% lung, and it also has a pretty high performance on the lung tasks. And then Panakea, which was trained on over 80% breast cancer. Actually, the breast model was trained only on breast cancer, but yeah, even though it's not so many cases, it's breast specific, and it seems to work really well on breast, even though it's a small model, and it was only 5,000 whole slide images. So it might actually make sense in some cases to maybe use tissue specific models. But of course, it's also nice to have one foundation model that is able to do all of these tasks equally well. And like another example here, again, Prof. Gigapath with bowel, also like 30% bowel lower GI, and then of course also in colorectal, then they're pretty high performance. But here again, it's not a perfect correlation with stomach cancer cases. It seems to be a negative correlation. So of course, there are many other factors that play a role here, but it's still something you need to consider. And especially if you do benchmarking and you want to know in general which model is best, then you shouldn't just test it on 1 or 2 cancer types, but probably include more. Still, I also looked at the performance for each cancer type individually, and here it was still usually the same models that came out on top. So it's also just one of many factors that play a role. And then the next question I wanted to answer is how different these foundation models actually are in the feature vectors they produce. And for that, I looked at inter-rater variability at Cohen's kappa scores. And for this, I did some majority votes. So I had 5 models for each foundation model, and so also 5 predictions. And I always use the majority vote prediction for each patient. So if 3 of the 5 models for a patient said that it's MSI and the other 2 said it's MSS, then I said that the foundation models predicted MSI for this patient. And then I did the calculated Cohen's kappa between all combinations of models. And as you can see here, that the highest similarity is between Uni and Panakea with a Cohen's kappa of 0.66. So they are pretty similar in what they predict. For those who are not familiar with the score, 0 means that there's no correlation, or it's just random. Negative would be that they systematically predict different things, and 1 would be that they always predict the same. And I also sorted the models by performance here again. So CONCH was the best model across all tasks, and flipped the worst model across all tests. And what you can also see here a bit, the general pattern is that especially here among the better models, it's a bit darker. So the Cohen's kappa is a bit higher. They predict more often the same thing. Whereas here among the models that perform worse, the Cohen's kappa is also lower, which is kind of straightforward because if you have two models that predict the correct label, then they of course also predict the same things. So if they predict the same more often, then if they predict the correct label more often, then it's also going to be the same prediction more often. But still, there are some big differences, like Hebrew and Kaiko, for example, here 0.28 similarity, and C-transpath and Dynamis L-path 0.55, which is pretty high as well, and maybe also not so surprising because they were both trained mainly on TCGA. In general, pretty similar models, and also CLIP and BioMed-CLIP, even though they were trained on different data sets, they have a similar architecture, and also the predictions seem to be pretty similar. Yeah. And then for some more interpretability, I looked at some heat maps, and here the newest models are not included yet. But yeah, I just wanted to see some general patterns, whether the predictions of the models make sense, whether the models look at the correct parts of the tissue, and also if there are some patterns that show that some models perform better than others. But yeah, here this is just some examples from non-small cell lung cancer subtyping, and here red always means that the model predicts squamous cell carcinoma, and blue means that it predicts adenocarcinoma. And for example, for this case here, this is the tumor area, and most models, they focus mainly on that area, especially like here, these models, they mainly focus on the tumor area, which makes sense for something like subtyping. You would want to have the equal distribution among the tumor area and not focus on the other part. But of course, there are some differences, like here some models focus only on a few spots, whereas others focus more homogeneously on the entire tumor area. And sometimes it's hard to see the tumor area actually. And yeah, so here it's the same thing again, mainly the focus on the tumor part. So it kind of looks fine, but also looks very different between the models, and also always different for each slide. So it's really hard to draw any general conclusions from heat maps. For example, here at MSI prediction in DAX, we have two slides with pen marks here and then also here. There are some models that seem to look at the pen marks, which is a bad thing. We would want the model to focus on the tissue to make a prediction and not on pen marks, because they don't really provide any information for that particular task. But they still do sometimes, but then only in a few cases. Then in other cases, you don't see any pen marks highlighted in the heat maps. Yeah, so it always varies. I also looked at CRC sidedness, and here are also some examples where the models predicted the wrong class with a cutoff of 0.5. And again, this time some other models that focus on pen marks. But yeah, that's about all I could find from these heat maps. And the last idea I wanted to try is whether ensembling foundation models improves the performance. So Here I tried two strategies. One is just concatenating feature vectors. So I took two foundation models, for example, CONCH and prognostic. They both produce a feature vector for each tile. And then I just concatenate the feature vector for each tile. And I actually used the prognostic slide encoder embeddings because these are a bit shorter and I was a bit afraid of overfitting. And CONCH is also pretty small. So both together have a feature length of less than H-optimus embeddings, for example. So yeah, I wanted to be safe here. And then the other thing I tried is ensembling predictions of multiple models. So for example, taking CONCH VHF2 prognostic and DynoSSL and looking at the prediction that each model generates individually, and then just averaging across these predictions and taking the mean across these predictions as the new prediction of the ensemble. And as you can see here, I highlighted the ensembles in these blue boxes as that performance improves a little, especially the average prediction of CONCH and VHF2 is 74.4% versus CONCH alone 73.6 and VHF2 alone 73.2. So it's a bit better, but not so much. And yeah, the concatenated version doesn't really prove the performance here. It's very similar to CONCH alone, and here in these cases even a bit worse than CONCH alone. Yeah, but I also wanted to see statistical significances of all these results of the ensembles and also of the individual models. And so I did the lungs test for the OROC scores. And I always compared the best individual model, so CONCH, with all other individual models and also with the ensembles. And what you see here, these numbers are p-values, and all the gray boxes means that there was no statistical significance using the lungs test. And if it was pink, then CONCH was significantly, like there was a significant difference and CONCH had a higher OROC. And purple means that there was a significant difference and the other model or the ensemble was significantly better. And I ordered them again by performance. And as you can see here, CONCH was more often significantly better than the other model for most single models. The only exception is Virchow. I think Virchow was 6 times significantly better, whereas CONCH only 5 times, but very similar. But if you look at some of the worst models, then that, for example, it's more than half of the cases where CONCH was significantly better. And for the ensembles, it was mainly the other way around. So usually the ensemble was more often significantly better. And as I said, the best one, the average prediction of CONCH and VHF2 was better in 7 or 8 tasks, whereas CONCH alone only better in 2 cases. So it seems to improve the performance a bit, but yeah, the differences aren't huge. So with that, I'm already at the end of my talk, and I just wanted to go back to where I started. So the standard pipeline in computational pathology. And we mainly talked about this step today. So how to get from the tiles to the feature matrix or feature vectors. And the 3 main takeaways, I would say, are that it makes sense to use multimodal data in training, even for UML applications, because even though CONCH used less data and is also smaller than many of the large vision-only models, it was still outperforming them. And that diversity is important in training foundation models. We saw that in the data set, it makes sense if the there are a lot of patients included, a lot of whole slide images, but also it matters that these whole slide images are from all kinds of tissue sites and that the distribution is also kind of balanced. And lastly, that with ensembling of foundation models, you can even improve the performance a bit more to go beyond the best individual model. And with that, I thank you very much for your attention, and I'm very welcome to take your questions.
That's brilliant. Thank you very much, Peter, for a really interesting talk. So I think there's a lot to take away there. So should we open the floor to questions? Does anyone have any questions they'd like to start off with? Yeah, sure. So got Peter.
Hi. I was wondering, why did you pick these specific cancer types and not any of the other ones?
Did you manage to hear that question? Sorry.
Yeah, that was mainly availability. So yeah, I try to include multiple cancer types and try to also include some proprietary cohorts. And so, yeah, that's what I had the data for. Yeah, so that was the main reason for picking these cancer types.
And on that point, do you expect all these results to generalize to most of the cancer types in general, or the messages at least that you
I think the general patterns are pretty similar because I didn't show it here, but I also looked at the performance for each cancer type, and yeah, it was the same model is usually on top. So I don't know now with VHF2, it might have been better somewhere, but before I added VHF2, CONCH was always the best model in breast cancer and lung cancer and stomach cancer, also in colorectal cancer. So probably it will also be in many other cancer types, but of course it would be beneficial to try them as many as possible. Yeah.
Yeah. I mean, I really like that slide on data volume versus diversity. So we often sort of think as long as we get as much data as we can possibly get our hands on and train a model, that we're going to have the best model. But well, your results are clearly showing that you need to have a good diversity too.
Yeah,
so that was it.
That's also like Biometric versus CONCH. The architecture is also different, but both based on PMC data mainly. And there in CONCH, they made pretty clear that they tried their best to focus only or to exclude the image caption pairs that are detrimental and only keep high quality image caption pairs. And it seems to have worked better. So it's definitely, I mean, it's also very hard to do that for those numbers of cases, but it's still beneficial if the slides are actually of high quality and diverse.
Yeah, definitely. Thanks, Peter. So we've also got a question from Craig Miles online. He said, fantastic presentation. Thank you, Peter. I wanted to ask if the transformer itself was optimized or if some standard architecture was selected. Also, was patch extraction MPP static for each foundation model? So I think is that the same size patch and resolution for each foundation model? And finally, how much compute was utilized this work? So there was 3 different questions. Did you get those? Sorry, Peter.
Yeah, I have the question open as well. So the first one, the first question, I just used the standard architecture in the STAMP. I didn't do hyperparameter search or anything like that. I wanted to just compare it in the standard setting that would also be used if you use it in the clinical setting. So yeah, I didn't do any hyperparameter search or anything like that. And yeah, the patch extraction was MPP static. I always use the standard STAMP parameters here as well. So we have 1.14 MPP, so that's close to 9 times magnification. Yeah, and how much compute was used, I'm actually not sure. I never measured it, but that's something that would definitely be very interesting because it depends highly on which foundation model you use. The differences between small models and like CTranspath, for example, or large models like ProgGigaPath, they are really large. So yeah, that would definitely be an interesting point to compare to put numbers to it. But for example, I know that if I take a large slide at even a higher resolution, then it takes up to 2 hours with H optimus 0, and then the same slide with C-transpath takes like less than 5 minutes. So definitely makes a difference.
And I've heard you mention Stamper a couple of times in this presentation. So can you tell us a bit more about what the actual steps taken there by Stamper? Sorry. So
Yeah,
this is a
so
series of
STAMP is
pre-processes.
it's just standardized. It was published in Nature Protocols. It's just a standardized pipeline end-to-end where you can you use some whole slide images, you put them into it, and then you can do the entire process from pre-processing the slide, removing the background, tessellating it into small tiles, and then doing the feature extraction with originally only C-transpath and uni were included. But I have another fork now with all the foundation models I added. And yeah, you can do the feature extraction, and then you can train aggregator models. And then you can do some statistics and also some heat map and top tile analysis with it.
Brilliant, thank you. We've also got a question from Yuri online that said, great talk. Were some of the diagnostic tasks related to segmentation, tissue or cell? And what is your take on using foundation models as encoders for semantic segmentation tasks, e.g. for multi-class tissue segmentation?
That's a good question. I saw some papers on segmentation, but the tasks that I use, they are not really related to segmentation, and I never really worked with it myself, so I can't really give so much helpful input for that question, I think. But yeah, I mean, that's definitely something that seems to work to some extent, and it's definitely something that would also be very interesting to look into in more detail and compare different models. But of course, also harder to get some metrics for it than comparing the foundation models just on some classification tasks.
No, definitely, that's definitely something that's interesting to try. Mustafa, I know you've asked if you can ask a few questions.
Hey, yes. Can you hear me now?
Yes,
Hello.
we can hear you okay.
Oh, that's all right. Well, thank you very much, Peter, for a really, really interesting presentation and great work, really well done. You saved us a lot of time, actually. So, I actually had a few naive questions starting from your from like some of your starting slides, and my mic wasn't working to ask. So you mentioned, so the first naive question is, you mentioned you normalized the results in the tables, in the heat map that you showed, right? Can you go back again?
Yeah,
And
I can go back.
yeah, and just clarify in my head. I want to figure out how the normalization was being done. Yeah, for example, in one of these.
Yeah, the normalization, how I normalized the table, or what was the question?
Yeah. You mentioned something about you normalize the results.
Yeah, so the thing is, if like in a normal heat map, you would just have one scale, color scale for the entire heat map.
Yeah.
But the problem is then that the main thing that is highlighted is the tasks, because there are just some tasks that are very like easy to get a high performance on, like for example, non-small cell lung cancer subtyping is a very straightforward task where all models have an OROC of above 0.95, and like other tasks are much harder. And so I changed it to row-wise normalization. So that means that in every row there is one model with a very dark color and one model with a very light color. So the scale here in the first row is from 0.72 to 0.92, and here, for example, it's from 0.56 to 0.7.
Yeah, that's my question. That was a little bit tricky to me. So did it just normalize for the sake of coloring, or the numbers showing are also normalized?
Only for the sake of coloring.
I
The
see.
numbers are, yeah, they are not
Are the exact numbers? All right.
numbers
Okay.
are
All
the
right.
real
All
numbers.
right. That's clear now. And you also reported results regarding the prognosis experiments in the same table, right?
Here.
Oh yeah, that's what was so how did you did these prognosis tasks? Is it like a classification?
Yeah, so yeah, sorry, I didn't mention that. It's only n 0 versus n plus. So basically, just that the lymph node is not affected, or any n plus n1, 2, and 4. So that there is some kind of lymph node metastases, or for
Yeah,
M status, then it's n0. So no,
I see.
distant metastases or anything M plus.
Makes sense. All right, thank you. Sorry, another. I have I have a few questions. Just feel free to stop me whenever.
We've got some time left, Mr. Fair.
Okay,
So
just okay. I'll ask the important ones first then. So you mentioned something about doing a statistical test
Uh-huh.
to find the significance of the AORCs. I failed to find where did you report them? Did you like all the results that have been reported? Are they all statistically significant? I'm talking about the DeLong test.
Yeah, I can go back to the long test. So I always highlighted the significant results. So always, when it's not great, then there was a significance difference.
Oh yeah. Oh, so you did it. Okay. So you did see. All right. So what I was wondering was, especially for the subgroup of tasks that you get, the low performing task where you reported them, right? So you get like lower AORCs for them, like around 0.5, 0.6, right? There are some statistical tests that you can use to find out that, because when AORC is low, there's a chance that you may not be predicting your desired variable at all, but predicting something else.
Yeah, yeah.
Like, did you like look into that?
I did it to some, or only on one task mainly, because I like a colleague of mine in my group was looking at something like that, and so I looked at BRAF, because in colorectal cancers there have been some studies showing that there are a lot of confounders, and so BRAF is a good example of that, where the BRAF prediction is mainly influenced by MSI status.
Yes.
So that's something I looked into, and yeah, definitely if you look at the subgroups, if you look at BRAF predictions only in the MSS subgroup or only in the MSI subgroup, then the ORG is quite a bit lower, but I didn't do it systematically.
I see. All right. Okay. I guess, yeah, I guess I'm all good. Thank you very much.
thanks, Mr. Fair. And thanks
Oh,
for
sorry,
answering.
Just another quick question. This M state, the metastasis state, is it available for TCGA dataset too?
Yeah, you can look it up for TCGA. I always had to find tasks where the ground truth is available for TCGA, because I always only trained on TCGA because I wanted to avoid any data leakage, because some of the foundation models were pre-trained on TCGA.
Fantastic. I hope, all right. I'll try to find it. If not, I'll send you an email.
So, Peter, we've also got a question from Mark. That's in person, sorry.
So first of all, you showed a slide for, I think, Virtuo 2, where you were showing how they were trying to make the distribution of the training data, yeah, this one more even. I'm just wondering, have they done that by sourcing more data for the less common ones, or is it a resampling strategy?
I think it's resampling, but I would have to look into the paper again. But that's a good point. Yeah, I think it's resampling.
Cool. And the other quick question. So you said that in this stamp pipeline, like you're extracting patches at around 1 MPP. So some of the foundation models, I guess, have been trained mostly on slightly different resolutions. So is it possible that some of the models are perhaps not performing at their best because the MPP, the patches and extractors aren't at their kind of ideal resolution?
That's definitely a good point, and might definitely be true to some extent. I mean, usually those pre-training algorithms, they usually do some cropping, and so even though like the original whole set images oftentimes are only at 20x, then by doing this cropping and resizing, you still usually get a variety of resolutions, but yeah, probably
quite robust to the MPP value.
But of course, only to some extent. So yeah, there might be some differences if you look at 20x, but it's also computationally then quite a lot more challenging if you run all the experiments at 20x.
Yeah, it's very true. Thanks.
Thanks, Mark. Thanks, Peter. So I think we've got time for probably one or two more questions. So I know, Peter, I know you've got another question. So, Kezi, you've got a question?
If I can ask, so there is a table in your paper shows the high performance and low performance comparison. So in the low performance, is that all because of the data is imbalanced and they are the rare cancer type, or so can you please analyze why there is a low performance for specific tasks?
Can you maybe repeat the question, Adam? It's
Yeah,
somehow
so
very
like
notable.
in your paper, there's a table compares all the model for some high performance and low performance. There's a table in your paper draft.
Yeah, similar to this one, right?
Yeah. So why do you think there's a low performance task for different models? Are they all because of the tasks are the rare case, like the rare cancer types, or I mean, do they have any common points for those low performance tasks?
I mean, it can be a variety of things. For some of the tasks, if it's very unbalanced, the classes, and then one group only has relatively few positive cases, then that might lead to a reduced performance. And if you have had more cases to train on, it might get better. But I excluded all tasks where there were less than 10 cases in the small class to avoid having those tasks where it's just not enough cases. But yeah, that might be one reason for it. Of course, also some of the biomarkers, they might not lead to morphological changes that are detectable, or only some very small changes that are very hard to find, and then the performance might be lower. Or yeah, maybe if there are no morphological changes detectable and it's mainly just a confounder, then it also depends on how often the confounder and the actual label you're trying to predict, how well they align. So if there's a high alignment, then of course the ORAC will be higher. And if they don't align so well, then ORAC will be lower. So there are multiple reasons for this. And for me now, the separation was just whether one model manages to get a score above 0.75 or not.
I see. Would you mind to go back to the first table you show in this presentation about the different for this one. I'm wondering because I think you're ranking from the first row to the last row based on the performance, right? Based on the score from 0.9 something to 0.7 something, like on the table on the left. So is that because probably that's a naive question as well, but different row have different case numbers, right? So do you think it's because the case numbers may affect the performance as well, or if you want to fairly compare different models, let's say I don't know exactly the last row, like DACHS, how many cases inside that one, but do you think it can be considered like adding a weight when you comparing those performance results? It's like maybe last row have the less weight, but the first row have most weight. Do you think is that going to maybe can be a confounder or influence on the comparison?
I'm not sure if I understand the question correctly. So you mean that if the performance is well, then it should be weighted more?
So I'm wondering, when you compare those models in different tasks, do you think it's fair if there's a originally exist class imbalance problem in different tasks? Or should we consider if you want to evaluate the domain generalizability across different tasks, should we trying to firstly balance those tasks or random select those tasks and then compare in different ways?
Yeah, if you balance the tasks, then that might definitely change the performance to some extent. I saw it especially with these experiments with less cases, like where I tried to train only with 75 patients or 150 patients or 300 patients. Then there were some tasks that suddenly didn't work at all anymore with 75 patients, and that was mainly, I think, because if you only have 75 patients, then there are suddenly only a few positive cases, and then that's not enough anymore. For example, EBV status prediction and stomach cancer was one of them, I think. The performance here is very high with like 0.88 for the best model, but with 75 patients, it didn't work at all anymore. And I think that was because there were too few positive cases. So yeah, having more of them definitely helps, I think.
Thank you very much.
You're welcome.
Thanks, Peter. I know we've gone over our time. Sorry, do you have time for just one final question? Peter?
Yeah, sorry.
Oh, sorry. I know we've gone over our time slightly. Do you have time for one final question?
Yeah, I have.
Is that okay?
Yeah.
Well then, sorry, Peter.
It's okay. Maybe it's a naive question, but for your statistical analysis, the heat map, I mean, sorry. Yeah, for this one. So I'm not familiar with this test, but do you have to adjust for multiple hypotheses? Like if I wanted to use this in my own research, would I have to do that?
Yeah, that would probably be better from a statistical perspective to do that. But yeah, this is just always a cutoff of 0.05, even though it is multiple testing, though you.
So this is not adjusted. So this table is not adjusted.
I didn't. Sorry, what did you say?
So this table is not adjusted.
This table is just with a cutoff of 0.05.
Okay.
Yeah.
Brilliant. Well, I think we'll call the seminar to a close there then. Thank you very much, Peter. I know we've had a lot of questions there for you to answer at the end.
Yeah,
so thank you very much for juggling all those.
Thank you very much for these questions. There were some very good questions.
And thank you everyone online for attending and for everyone in person. Our next seminar will be on the 4th of November. We're joined in person by Jack Breen, University of Leeds. So yeah, thanks again, Peter. Really appreciate your time and hope you have a good rest of the day.
Thank you. You too.
See ya.
See you. Bye.